Hi, everybody. As folks come in, we just have our introduction slide up. Again, this is the New Energy Conversations with Early Career Energy Researchers, co-sponsored by a bunch of different universities to highlight the work of emerging scholars, assistant professors. And today is the first day that we've actually had senior graduate students presenting. So I'm really excited today to have Wester Schoonenberg and Steffi Muhanji from Dartmouth College. And the talk today will be on interdependent energy infrastructure systems. We'll first hear from Wester, we'll then hear from Steffi, and then we'll have questions. As always, please feel free to type in the Q&A box your questions, and we'll be taking questions at the end. I'm going to turn my camera and mic off and turn it over to Wester. Thank you, everybody. We're really looking forward to this talk.
Awesome. Thank you very much, Elizabeth, for introducing us. I will go ahead and share my screen. There we go. So that should work. Thank you, everyone, for being here today. I'm really excited to talk to you about our work in interdependent energy infrastructure systems. As Elizabeth mentioned, we'll be presenting together, Steffi and myself. And yeah, we're part of the same lab at the Thayer School of Engineering. Today's discussion, I'll start off with a brief introduction, and I'll ground the discussion in some of the major trends in the energy landscape. After that, I will talk somewhat more in depth about the work that I do in modeling these interdependent energy infrastructure systems with heterofunctional graph theory. And then I'll hand it over to Steffi, and she will speak about her work with the New England Energy Water Nexus and enterprise control. And afterwards, of course, there's going to be time, and I'm looking forward to the discussion at the end. So a quick introduction, my name is Wester Schoonenberg. I'm a 6th-year PhD student over at the Thayer School. Steffi, my colleague, is a 5th-year PhD candidate at the Thayer School. And together, yeah, so we're working in the LINES, the Laboratory for Intelligent Integrated Networks of Engineering System. It's a mouthful. And we specialize in studying networks of cyber-physical engineering systems. The engineering is really interesting and really cool, but we always operate within a political context. And so life cycle properties are essential to the work we do. So we look, life cycle properties really look beyond the merely technical performance, but we also look at safety, resilience, robustness, reliability, sustainability, etc. These systems are really integral to society, and we really should analyze them as such. We work with 5 different application domains in our lab, and Steffi will be highlighting smart power grids and the energy water nexus. And I'll be speaking about my work in industrial energy management and integrated smart city infrastructures. To ground the discussion, I'll briefly mention the 5 forces of change that are critical to the work that we do in the changing energy landscape. So we have, of course, a growing demand for electricity. We have an emergence of renewable energy resources that are specifically distributed in nature. We have emergence of electric transportation and all of the new dynamics that are introduced to the grid as a result. For example, vehicle to grid. We have the 4th trend is deregulations of the power market, which drives a revision of the energy value chain. And finally, there's innovations in smart grid technology that really activates the edge of the grid. And so the where and how of energy consumption is changing fast. And Steffi's work will take a closer look at how to handle all of these forces of change for the power grid and how to leverage the energy water nexus to manage these forces of change and manage the changing landscape. For my work, it's, especially my work in smart cities, it's important to note some trends in urbanization as well. What we see is that there is a global increase in population. We're expecting almost 10 billion people by 2050 on the planet. There's an increasing percentage of people that moves to urban areas, and there's an increasing need for sustainable and resilient infrastructure. The majority of megacities in the world is located in coastal areas, and so these areas are prone to hurricanes and flooding. And so we need to figure out how to make all of this infrastructure and how these urban areas more resilient and sustainable. And so with this trend of urbanization, we also see that space in cities just becomes really short. We have less of it. And frankly, we don't want to give the space that we have to infrastructure or energy infrastructure. And so the space for energy infrastructure is also decreasing. And as a result, these infrastructure systems become ever more interdependent. And how does that look? Well, this is a picture of 1955 in New York City, where the L train that is now decommissioned is running over the street. And you can really see, and it is an old picture, but it really demonstrates well how all of these systems are interdependent just as a result of density, right? We have streetcars, we have cars, we have pedestrians, and an elevated train all running within the same space on the street. Furthermore, the interdependence is also a result of a drive for sustainability. The New York City transit system is electrified, and as a result, it's dependent for its operation on the functioning of the power grid. And this is something that you really saw during Hurricane Sandy, where they tried to evacuate Lower Manhattan, but as a result of the rainstorms ahead of Hurricane Sandy, the power grid was already knocked out and the trains didn't run anymore. And it turned out that they had problems evacuating because they simply didn't have enough transportation capacity to get everyone out because the trains weren't running. And so I'll circle back to what I said at the beginning. Life cycle properties are essential to understanding these interdependent energy systems. The downside of these life cycle properties is that they're really hard to manage, and so for example, resilience is a property that is really hard to measure. And so what we need are some new approaches, some new tools to analyze energy systems, and specifically interdependent energy systems. And so what Steffi and I have in common with our work is that we both use mathematical models to represent the real world systems. And we use those mathematical models to inform policymaking or decision-making in the real world. And so the models that the theory that I'm using is heterofunctional graph theory, and Steffi will be speaking today about her work with enterprise control. So what does it mean, somewhat more technically speaking, for these, how do you address the problem of resilience in these interdependent systems? Graph theory has really been used, so networks have really been used to look at these interdependent, or have been used to look at infrastructures in the past. And so on the left, you see an example of a graph, right? You have a couple of nodes and some connections between these nodes that indicate how power can go from, for example, a solar farm to a house in the top right, or a water treatment facility up here in the top left. Now, the downside of these graphs is that if you have rooftop solar on the house here, it really doesn't show up. And so when you study resilience, and if you knock out this power line, you would assume that there's no power going from the solar PV plant to the house. But the house, I just said, has a rooftop solar. And so the house still is able to actually function and have electricity. And so conventional methods haven't really been able to capture that new massive trend in power grids. And so the study of resilience for power grids has been really tough to do with conventional graphs. And so this is where my technology or my methodology of heterofunctional graph theory comes in, where we take a slightly different look at graphs and we couple function and form. So we impose that, oh, we have rooftop solar on this house. And so we have an extra node that shows that we're generating power at the house to provide to that house specifically. And then without getting much more technical than this, I'll show that we can do this at a fairly large scale. So the first major application that I came up with to demonstrate this is the work in smart cities. So we have a water distribution system, we have an electric power grid, and we have an electrified transportation system that you should imagine as being superimposed on top of each other. And all of these systems are connected. because we have our water treatment facilities that require power to operate. And so in order to provide water to the houses in your smart city, you need power. And if you have electric vehicles, then you need power in order to charge those vehicles and to provide the service of transportation. And with my theory and with my methodology, I can create a single mathematical structure to analyze all of that at the same time. And because I'm not going to talk about the methodology in too much detail, I'd like to refer you to the book we've published on that. We can take an even larger scale of problems. We're currently looking at the American multimodal energy system and working on a resilience study for the American multimodal energy system. So what does that mean? We've got oil pipelines, we've got a power grid, and we've got natural gas pipelines. All of those energy infrastructure systems are interconnected and dependent on each other. And the great example was, of course, given, I believe it was the winter of 2017, when there was a shortage of natural gas in New Hampshire, or specifically in the New England region. There's only really one big natural gas pipeline coming into New England, and that natural gas needs to be used both for heating homes and for generating electric power. And so both the power grid and the home heating system are dependent on that one pipeline of natural gas. And if you run into a capacity limit on that pipeline, you're going to have brownouts, and that's exactly what happened in 2017. And it only became apparent because this extreme case was happening. And so what we try to do with our models is try to predict if and when those cases will happen. And so we do a lot of this work, and it's all static, right? We look at a structure of a system and we see where the weaknesses are. But what we can also do is impose dynamics on those systems. And this I've done for industrial energy management, and I've specifically applied it to a microgrid-enabled production system. And it looks something like this. We have a factory floor with a couple of machines that machine a bird feeder. And I've coupled a microgrid to that with renewable energy. And with heterofunctional graph theory, I was able to model that system and get some really interesting results. And so what you can see in the top figure is we have renewable energy power generation of one wind turbine and the aggregate for the two wind turbines that I have in my system. And this blue line indicates the net power consumption of the grid, of the microgrid. And so whenever the machines are on, we need to import a lot of power. So the slack bus is generating positive megawatts. But whenever the machines turn off, because maybe the product is being transported from one machine to the next machine, the energy demand drops, and we're now all of a sudden putting renewable energy back into the power grid through a negative slack bus. And when we assume some carbon emissions for this slack bus and for this power grid connection, we can also calculate the CO2 emissions based on the production schedule of this factory. And so that concludes my work with using heterofunctional graph theory to study these interdependent systems. And I'd like to reiterate, right? Resilience is key, and the life cycle properties are key to measure, and we need a new set of tools to do those. And that's exactly what I've been working on during my PhD. Steffi will now take a slightly different look and a more detailed look at the power grid, and we'll also talk about renewable energy integration and how to work with the energy water nexus to enable that. Are you ready, Steffi?
Yes, thank you, Esther.
Sure.
Okay, can you see my slides?
Well, good.
Okay, so I will be talking about the New England Energy Water Nexus, and the goal of this presentation is to just give you a highlight of the results from the ICE New England Energy Water Nexus study that we conducted last year. So as Wester mentioned, it's really important to start thinking about how to model interdependent systems. And this picture here shows how well, how coupled the energy and water systems are, especially in New England, where you can see most power plants are located near water resource. And so we have to start thinking about ways in which we can model this. And this is particularly important when we are thinking about renewable energy integration. So something else that Weston mentioned is that the power system is changing. And specifically, we see this in the supply side, where in the past we would have well-controlled generators, but now with solar and wind, we're seeing that a lot of this control is lost and is being replaced by variable generation. And a slightly another different change on the demand side is that we have an increase in demand side management, and this provides a new control lever that power system operators can start leveraging when it comes to renewable energy integration. So usually a system operator would dispatch generators to a forecasted net load, where net load here is the demand minus all the variable generation in the system. And usually this forecasted net load is not, does not match perfectly the actual load. And so dispatchable generators must track the forecasted net load in real time to ensure that the system is balanced. Another challenge that we see is this dark curve. I'm sure you've all seen it somewhere. And the black line here is the demand curve. And as you add more solar to your system, you find that the belly grows. And what's really interesting is at the bottom of the dark curve, where your solar generation is diminishing and people are going back home, turning all their electricity consuming devices online. And you have to bring up all these generators to online so that they can meet the diminishing generation. So this can be challenging to system operators. And so in a sense, they need a lot of various control levers to help them manage the grid, especially with the net load being so variable. And so I'll be talking about three of this: the load following, ramping, and regulation reserves, which are used to track the variability in net load. And in some cases where you don't have enough reserves in your system, or there's negative net load, you might resort to curtailment as a means of controlling, of balancing the grid. So load following reserves represent how much the ability of the generation fleet that is online to move up or down. And so in case you had a 400 megawatt generator, and this generator has the ability to ramp up 500 has a maximum capacity of 500 and a minimum capacity of 200. This generator can provide you with about 100 megawatts of upward load following reserves and 200 megawatts of downward load following reserves. Similarly, ramping reserves represent the ability to move up or down with your generation fleet in time. And so if you had a generator that could ramp at 25 megawatts an hour, this generator can provide you with 25 megawatts an hour of upward and 85 megawatts an hour of downward ramping reserves. Regulation reserves are slightly different in the sense that they are an automatic feedback control that some generators have, and this is that to give them the ability to track the net load. And so it's slightly different in the sense that it also acts at a much faster timescale. And all three of these reserves quantities are used to balance any net load variability uncertainty in the real time. So as the demand side changes, we have to start thinking about ways in which we can leverage demand side management to provide these types of reserves to help balance the grid. And this study is looking specifically at how to use the energy water resources, which are mostly on the demand side, to provide this control to power system operators. For this study, as mentioned, I used the Enterprise Control Simulator, which is an in-house simulator with 4 layers of cyber control. We have the day-ahead resource scheduling market, which is determines generators for the next day. And the same day resource scheduling, which is very specific to the ICE New England operation. And this runs every hour and just dispatches generators that are fast start. And then finally, we have the economic dispatch, which is a 15-minute optimization, runs every 15 minutes. And it does not bring online any generators, but instead it changes the set points of online generators to help balance the net load. And regulation services on top of all three to take care of any remaining imbalances in the system. Given the complicated network of the ISO New England grid, we use the pipe and bubble model, which was agreed upon by ISO New England stakeholders. And the bubbles here represent the load zones. And we have, they're connected by tie lines and interfaces that also enforce line congestion limits. And we implemented a lossless DC power flow to determine the flows between the bubbles. In order to study the energy water nexus, it's important to be able to quantify the flows of matter and energy between the three physical infrastructure, the electricity and water, as well as the natural surface environment. And with the pipe and bubble approach, every water utilities can be able to fit within a bubble, and in a sense, we didn't need to do a full hydrological modeling for the study. So the EPECS simulator was enhanced, so we could be able to quantify emissions, water withdrawals, consumptions, and all that. So we looked at two operating modes, the conventional and flexible operating modes. Conventional did not have any flexible energy water resources, while the flexible modes, we had the ability to obtain reserves from run-of-river and conventional hydro, and wastewater and water treatment plants had this load shading capability. And we considered 6 scenarios for each of this. So we worked closely with NREL to come up with this data, which was derived from the 2030 scenarios that we used for the ICE New England study. The two main scenarios to note here is scenario 2040-3, which has a high penetration of renewables, and you'll see why that's important on the net load, the next slide. And scenario 2040-4, which was the business as usual scenario if the ICE New England system were to evolve at its current pace. So this is just a depiction of the net load for the business as usual scenario at the top, where you see that the net load is never really zero. But in the high renewable scenario, we have that the net load is significant, is mostly below zero. And this is because you have so much renewable generation in your system compared to demand. And so you have to resort to curtailment of those renewables. So just to highlight the results from this study, in order to assess the reliability value of this flexible energy water resources, we looked at balancing performance of the grid, the environmental performance, as well as the economic performance. And we see that with the flexible operation, we're able to increase the overall amounts of load following and ramping reserves. We also reduced the amount of time curtailment was used as a control lever. And so this resulted in overall higher use of renewables. And as a result, we see that water withdrawals and consumption by thermal power plants for cooling purposes is also decreased. And CO2 emissions are also reduced. And overall, the total cost of production is for the day ahead and real-time market also decreased significantly. So to conclude, we see that flexible energy resources are shown to enhance balancing performance, environmental performance, as well as economic performance of the grid. And this is particularly important because it shows that there's a lot of flexibility benefits that can come from viewing the demand side as a control lever and engaging these resources to help support the grid, especially when you're thinking of systems with high penetrations of renewable energy resources. And so when we think about demand side resources, most of them live in the distribution side. And so we have to start thinking about ways in which we can design resilient distribution systems and also markets that allow us to leverage these benefits. And my current work is looking at working with the city of Lebanon. And we are designing a distributed transactive control system to study to help model their municipal aggregation. And we've also published a book on how to leverage the large number of energy Internet of Things at various levels of the grid infrastructure. With that, I would like to acknowledge our collaborators and thank you for listening. And here are some references.
Thank you so much, Steffi. That was really great. And I think that this was the grant that you got from the Irving Institute, right? That funded your work with Lebanon?
Yeah, so the Irving Institute is funding the Lebanon work, and we're really making very good progress on that, and with some results to show very soon.
I'm really excited about that. Thank you both for your super presentations. Audience, please feel free to type questions into the Q&A tab below, and I'll be moderating the discussion. And I'd also like to have this be more of a discussion among you as well. So Wester, if you could think of a question for Steffi, and Steffi, if you could think of a question for Wester, we'll start. But one of the ones I wanted to start with you, Steffi, I'm on a national grid study right now, and one of the conversations around the Internet of Things are cybersecurity risks. And I'm wondering, from your perspective, how would that affect or change some of your analytical frameworks or thinking about this? How would you address that within your context of thinking about Internet of Things as a demand side management resource?
So one way that we are trying to deal with cybersecurity risks is modeling, especially for the distribution system, is starting to think about distributed control as a way of modeling these markets. And this significantly reduces the amount of data that you're passing to a centralized agent, and takes care of the privacy risks that come with a lot of data sharing. And so with distributed control, you can start thinking about modeling your system in such a way that you're only sharing very little amounts of information, that even if they were intercepted, somebody won't be able to get the full picture of the system.
And I think one of these risks was also of the Internet of Things affecting the management of the grid.
Internet of Things affecting the management of the grid.
The idea of a malacting person controlling some of the demand devices and by therefore changing grid operations. So not necessarily the privacy piece as much as the Internet of Things being taken over by hostile actors and that changing how the grid operates.
Yes, so that would become an issue in terms of how much data you're passing. And so you have to start thinking about these devices and what they are connected to and how much data these devices are passing to the cloud. And so you have to design your system in such a way that attacking a single device does not impact the entire system by reducing the number of the amount of information this device is holding about the overall system in general.
Right, and especially if you're talking about— I wanted to
ask Wester for cities and for industry as well, if you could answer the same sort of question.
Yeah, I think any person that's part of the energy system, right, owns a couple of devices that all consume power. But each of those devices you would need to hack individually in order to turn it off or turn it on, which means that you have to hack millions, if not billions, devices in parallel, and then all turn them on or off at the same time in order to cause a disruption from the demand side.
Isn't that just called like an update of your software?
If it's pushed by, it depends, right? If you manage to hack Apple or Google, right, and you can turn all smartphones that are being charged on or off at the same time, then maybe. But generally speaking, each of those devices need to be hacked one by one. So that is, I think, the main thing, because any one device just doesn't have a major impact on the grid. And
no, I think the idea was that you would have, kind of multiple control through some sort of, scheduled update that would then, sit there and allow for, but from an industry perspective, I know this is big. And from a grid operator perspective, I know this is something they're managing. How does that play out in a smart city context in terms of smart city and thinking about our interdependent infrastructures?
Well, I mean, you have your centralized controller, right? And if you think about, for example, the control room for the transportation system in New York, it is about as well defended or secured as the ISO New England control room. And they also have a backup control room. The interesting part with transportation systems, for example, is that they are that their control is still distributed because they're simply older. So if we talk about the transportation system in Chicago, there is a central control room, but nothing is actually controlled from that room. They call people, the linemen that are at the ends of the lines, to flip a switch, right? So if a train needs to switch tracks, someone needs to do that manually alongside the track, and it requires a phone call on a secure line to do that. So the systems are so old that you cannot hack into them over the internet. And so,
for our old North American infrastructure, in Europe and Asia, of course, the infrastructure is more fully automated.
Exactly.
So one of the stories I really appreciated you telling was, when Superstorm Sandy hit and how hard it was to do the evacuations out. And I remember talking to grid operators around that time, and they were really happy that they kept the power on above 42nd Street with the recognition there's not much you can do if your substation's underwater.
Absolutely.
And so for both of you, this idea of our energy infrastructures in the face of a changing climate, for Steffi's case, in Upper New England, we expect more drought and more extreme precipitation events. How does that affect kind of this water as resource? How would we need to think about it differently? And in Wester's case, this idea of our urban infrastructure is oftentimes not built for the world we're going into, and how these types of approaches just help us, the audience, walk through these different cases and what a changing climate means for your different infrastructures.
Sure. Do you want to take it first, Steffi?
Sure. In terms of thinking about water security, right now it's really, New England is water rich in a sense, and so we don't really think about it as needing to control their water supply as much. But when you have droughts, the amount of the water that you'll be drawing in for cooling purposes is going to be at a higher starting temperature. And this also affects the ability of your thermal power plants to cool down. And so you might not have access to them when you need them in the summer months to support all the AC that everyone is blasting. So you have to consider the possibility that you won't always have these resources that you've relied on heavily in the past. Another challenge with, I've completely forgot my train of thought. Wester, you want to take it? And
Sure. So a couple of things. I think that people that make decisions about these infrastructure systems are changing their mind, and Sandy was definitely a catalyst for that. I was speaking with some of the people at the New Jersey Transit, and they have been redesigning the way that they connect to the power grid. So, which means lifting substations up 7 meters in the air, right, and literally building it on top of concrete pillars. what I see in the Netherlands, in my home country, is that one of the problems there is not necessarily keeping all the water out from the sea. We got that pretty well under control, but now it's very much, how do you deal with the rainwater that falls in these urban systems? Because a lot of the city infrastructure is paved, right? We have asphalt everywhere, and as a result, it's hard for rainwater to drain away from the streets, and you get these floods that put streets underwater. And so you need to think about, how do you handle all of that rainwater? And one of the ways they do it is they have these sunken in basketball courts or parks that are a couple of meters below the rest of the streets. And those are used as overflow basins, more or less. So when it rains, they've designed the streets in such a way that the water runs off to this basketball court, which you don't really need during a storm. So that from that basketball court, it can then drain slowly into the earth. So those are two ways of kind of, yeah, making next steps towards redesigning urban infrastructure and thinking about all of those different pieces.
I'm waiting for questions from our audience. The one that we have is asking from Brendan Daly, what does the forecasted and actual figure look like these days with many folks working from home as opposed to in the office? I think this was a demand question.
I think that's for me.
Feel free to share your slides again if you want. We actually had a bunch of students look at this over the summer. They looked at all of the energy shifts at RTOs during COVID times. And it was really interesting because it varied significantly by RTO. And the story for like even downstate New York versus upstate New York was really different. So here's forecasted versus actual load. Talk us through this.
So this figure here was, I think this is 2019 when we did this. And I can't speak for any figure that I've seen these days, but the one I saw earlier during lockdown, with everyone working from home, we found that this curve is a lot more flat in the sense that you don't have this dip, and when everybody's at work and you have and then you have this peak at the end of the day when everybody comes back home, and instead you have this more flat curve that represents people, like almost like a weekend curve when everybody is at home.
The other thing that was really funny was it shifted later. So everyone stayed in bed a little bit longer.
Yeah.
No one got up and went to work. And so that shift, but yeah, you definitely had huge switches between residential load, commercial load, and industrial load, with commercial load at those times. I think in New York City, it was down about 14%. And upstate, it was like 5 to 6% down, but you're right, it was the peaks that were off. And that really also affected the energy prices. So even though the peaks were only off 5 to 10%, the energy prices were 25 to 35% off. The whole report that the students did is online, but you're right, this is really interesting to think about how something like COVID affects it. And I just got a few more questions in. Resources to react to the grid's needs.
I lost
the sound as well, but I can just read it from here.
Yeah.
How far off are these benefits, and is there significant control, hardware, policy upgrades that need to happen to enable it? So as I mentioned, itself. It was just really the way you treat the devices or these resources in the energy markets. And so instead of just resorting to curtailment, why not think of curtailment as this useful thing that you can use to provide ancillary services, for example, or following reserves. And by just shifting the way you treat these resources in the markets really changes how much, like the balancing performance of the system in general. So there is some control changes that need to happen. And mostly it's changing the mindset of operators to start thinking of these resources, not just as a nuisance and super variable and causing trouble, but more of things that they can use to also balance the grid. In terms of policy upgrades, I would say that we need to start to give renewables a fair chance to participate in these markets, and so that they're not curtailed, defeating the whole purpose of having them in the first place.
So Steffi, one of the friendly questions that I have on this is, I've really appreciated that RTOs are sometimes their own kind of balkanized logic. How, for example, would new transmission lines from Canada or from even the Midwest potentially change this value proposition within the New England market?
So
would it make it cheaper? Would it make it easier to integrate renewables? Would it make it less profitable for a water resource?
Just speaking for this particular study, we looked at topological, not just topology as well, but also geographic situation of renewables. For when we did the first data, the renewable energy integration study, we placed a significant amount of wind generation in northern Maine. And well, that's where the wind is. But the biggest load centers in New England are in Boston. And so you have to transport that wind generation somehow to Boston. And so that's one of those areas where having transmission upgrades could really improve how well you utilize the renewables in your system. And so we were able to show that this is an issue that could, while you can shift the way you manage the system, upgrading transmission might be also needed, especially if you want to utilize your resource rich areas for generation.
That's a really important insight. Do you have a question for Wester?
Yes. You mentioned that you can model a behavior using heterofunctional graph theory. Do you want to talk a little bit about that?
Yeah, sure. Let's see where to start. So the idea of heterofunctional graph theory is that so what we can do with heterofunctional graph theory is you can make a structural model. So all the different elements of your system, so the combination of resources with their processes, with the functions they perform, are all like small elements to the system. And if you couple all of those elements together, that together forms your mathematical structure. For each of those elements, you can actually describe the physics or approximate the behavior using physics for that specific element. And so if you impose one or two equations for each of those little elements in your system, and then couple all of those equations together using that graph, that is how you can kind of build the behavior for the system as a whole out of all of its different elements. And so when you want to predict how a system is going to change or how the behavior of the system is going to change if you intervene or if you change the system itself, then you can simply take out the elements that you want to take out, you put in some new elements with their own physics, you hook those up to the existing elements that were still in the physics or in the model, and then you can run a new simulation to figure out what the new behavior of the overall system is going to be. So heterofunctional graph theory really focuses on breaking it down to the bare elements, imposing physics on each of those elements in the system, and then simulating the behavior as a whole by combining all of the physics for all of those elements together. Is that about right?
Yeah.
Yeah, and I think this is really interesting to think about, having kind of an optimal approach that brings this all together. And at the very beginning of your talk, I really appreciated how you situated your work within kind of policy environments that were really important for our society's critical problems. And I appreciate that a lot of these decision authorities are resting in very different departments with very different ideas of operations and budgets and things like this. And so I'm just wondering, from your perspective as someone who's going to be engaging in this work, how do you see this theory potentially influencing practice, and where do you see some of the potential barriers there?
Yeah. Steffi, would you mind if I share my screen again briefly?
Yes, of course. You should be good to go.
And it's great having you guys. You're doing a super job. I really appreciate this conversation.
Oh, I lost the Zoom. Let me see. Where did Zoom go? Yeah, it's on my computer.
And I think the same thing is true for you, Steffi. I mean, you know, the rules within an RTO are negotiated, some of them being easier to change, some of them being harder to change. I mean, from your work, where do you see some of the, you know, where theory provides insights into practice and where it might be a little bit more challenging to adopt? There he goes. He can answer first and then we'll go back. Okay.
Yeah, so what you can see is these are all the little elements that I was talking about, all these nodes, all these points in this awful complicated graph. Those are all the mathematical elements. And what I can do is I can create, I can add control agents to this graph and couple each of those elements in my system to a controller agent to figure out what the jurisdiction is of each of those controllers over what physical piece. And so what you can do is you can run, potentially you can run simulations where these controllers have their own interests, right? One is trying to, or they all are, for example, trying to reduce costs as much as possible, but one of them is also trying to reduce carbon emissions as much as possible. And so through an optimization program of such a dynamic model, you would be able to see how the controller agents manipulate their own little physical elements for their own best interest. So that is how you could, you know, if you take a step back and look at the system as a whole, then that is how you could simulate the behavior of the different agents. That kind of studies you can always, I mean, then you're really entering this area also of agent-based modeling, right? And negotiations between agents to get things done. And this is a more centralized approach, whereas agent-based modeling is a more distributed approach to that. And how does this inform decision making? I was talking with Andrew about this briefly. If we can simulate the behavior of these systems, and for example, we price carbon appropriately, and if we're looking, for example, at integrating hydrogen into as an energy carrier to, for example, clean up our ammonia production, and if we use electrolysis to produce hydrogen that we can use to produce ammonia. With the right carbon pricing, we can figure out at what point it becomes feasible from a financial perspective to produce ammonia from green hydrogen instead of from methane. And so these kind of models can help you by with determining what that carbon price should be, if you want to set that carbon price, or if that carbon price is the result of a negotiation.
And I would argue that there's probably even a more useful thing if you had different groups of city managers in the room and they were able to tell you where your assumptions made sense, where they didn't, and you were able to relax some of the optimization assumptions to kind of help them appreciate the ranges of different scenarios that can lead to, you know, within a certain area, different types of configurations of the solution space. And so while the optimal solution is beautiful for theory, for practice, getting real practitioners in and using these tools in a more deliberative process might be an interesting way to kind of extend the work further. And Steffi, for you, the work with Lebanon might provide also some interesting insights into this kind of, you know, theory meets practice, working with your municipality there. Do you want to speak a little bit to that?
So the work with Lebanon has really been very helpful for me to
Lebanon, the city, not the country. Just so everyone's clear, this is Lebanon, New Hampshire, not Lebanon, Beirut.
Yes, Lebanon, New
Okay,
Hampshire.
so Lebanon, New Hampshire.
To start, New Hampshire just passed their municipal aggregation bill last year, and so most counties can do a municipal aggregation and basically bypass the utility, purchase from the wholesale market directly, have real-time prices or various pricing mechanisms for their consumers. And as a result, you have a whole different way of thinking about the distribution system, where consumers are able to trade with their neighbors, or and you're able to also introduce more renewables locally and have more consumer engagement. And so when we started this work at Lebanon, we ended up spending a lot of time basically understanding, getting an understanding of what the city wants to do and what their needs are, and also what we can do as academics to support local communities. And I would say it was mostly a learning experience for us. When I was joining the project, I hadn't really worked with distribution systems. And so we've spent a lot of time getting to understand what Lebanon needs and how that how our theory in the lab can translate to support the needs of the community. And something that also came out of this collaboration is based on the Senate Bill 284, which is the data aggregation platform. And so we've been working with them to try and design a data platform that gives us enough data that, like, the right data inputs, so that they can be used to inform decisions at the business case level, at the municipality case, and policy level, and also something that researchers can tap into and do various studies. So it's a humbling experience to really see community members, some of whom don't have like an energy background, really, but mostly are passionate about sustainability and climate change, coming in and working on these efforts to try and push the community forward in the sustainable energy transition. So yeah, I think there's a lot to learn from both the academia, the industry, as well as the policy side. A lot of patience is required. But I think these types of collaborations are really important, so that the academic work does not go just stay in the journal papers, but actually gets implemented in practice. And we've seen this with our work with enterprise control, which has also been able to help inform decisions around economic studies for ISO New England. So I really think
perfectly into the, I was saying, this leads perfectly into the next question. And then after that, I wanted to ask each of you to give about a 1 minute kind of big picture thoughts for the audience. And then we'll be wrapping up after that. So the final question is from Scott Lehman. Steffi, in your Internet of Things work, what do you see as the biggest challenges for bringing these distributed DR resources to the wholesale markets? Metering, market constructs, economics? I thought this was a nice lead in from the previous discussion you were having about translating theory to practice.
So I think IoT, when we think about the Internet of Things, we have the technology there. A lot of us have some smart device at home. So the technology is not the problem. There's a trust issue that is associated with having so many devices that are not entirely in your control in critical infrastructure like the electric grid. And so we need to start thinking about who are the stakeholders and how can they work together to make this happen. And I think that is where the biggest challenge is. I always say that regulation also needs to catch up in this kind of space. And that would end up informing some of the market constructs as well as the economics. But I think the stakeholders, we need to start bringing the stakeholders together to the table to have these conversations about how to create interoperable systems that can support the grid at various layers. So yeah,
I'll go to Wester for his closing statement, and then you for your closing statement. I'll give you the last word, and then we'll wrap up. So Wester, about a minute and a half from you, and then a minute and a half from Steffi. Your big thoughts, what you want to leave the audience with?
Yeah, sure. You know, energy systems are just, they're interdependent. They depend on each other to provide essential services. And so really think about these energy systems as interdependent when you move forward in your work or in your personal life. And also think about when you're working on these systems, right? Think about the life cycle properties. Don't just focus on cost. Don't just focus on performance, but think about, I mean, sustainability is the obvious one, but think about resilience, think about robustness, think about safety. Those are essential as we're working with these critical infrastructure systems.
Thank you very much. Steffi, last word to you, your minute and a half wrap up.
Everything you just said. And particularly when we're thinking about climate change, resilience is becoming a much bigger issue that we have to consider, especially when we don't necessarily have control over what will be happening in the next few years. And so thinking about this, just adjusting the way we think about the system, the energy system in general, can really have major benefits. And I've shown that with just like really changing the way you view renewables in the market or energy or resources, you can have significant changes. So it's really important to start thinking of the systems holistically. Where can we improve and where can we get these benefits? So yeah, and also stay safe out there. That's it.
Yeah. I really want to thank both of you. This is the first time we've had graduate students on these series, so double thumbs up. You've set the bar really high for everyone that's going to come after you. So thank you both very much. And Stephanie Garcia, if we could have the slide of upcoming events. We're trying this term to really focus a little bit on kind of energy society, with the realization that there's an election coming up. Next week will be Jenny Stevens, Why We Need Anti-Racist Feminist Leadership on Climate and Energy. She has a new book out on this topic. Diana Hernandez from Colombia, Energy, Poverty, and Health in a Changing Climate. She'll be the next speaker on this series. She's a assistant professor at Columbia and has done a lot of research in her communities in New York. And then Leah Stokes from Leah Stokes is from University of California at Santa Barbara, and she'll be talking about short-circuiting policy, interest groups battle over clean energy and climate policy in the American states. She just had a great piece that came out on Vox on this topic as well. So, you know, as we're gearing up for the next couple of weeks, I want to thank Wester and Steffi for participating in this series and invite you all, of course, to our events going forward too. Thanks, you guys. We'll see you hopefully sooner rather than later. And like Steffi said, stay safe, everybody. Bye-bye.
Sounds good. Thank you very much.
Thank you.
Thanks again.
Bye.